Okay, let me get to the residue theorem, which is a very, very important concept of complex analysis. I could argue this concept is one single most important concept for people who want to use complex analysis to do integral and other things. For instance, for physics, it's, doing Landau damping involving on calculating the residue of a certain poles. The theorem said as such: if you want to do a loop integral, the loop integral can, in the complex plane can be written as the sum of all the residues multiplied by 2 pi I, and it's the residue of the function at pole a, ak. This is basically the pole in this concept is in a way a singularity. The formal way of calculating the residue is such: the residue of function f at a location c is 1 over n minus 1 factorial at the limit when z go to c to the n to the n minus 1 order of derivative, and derivative of this function multiplied by n to z minus c to the nth power to the multiplied by fz. And I will show maybe a little bit more examples in the future, but there's another way for the function that from the complex variables and applications, page 243. That book is very, very good books for people who want to use complex analysis in STEM most of the time. And fz equals to is in the form of fz equals to phi z over a polynomial at z minus z naught to the mth power. M is a positive integer. The residue of that for m equals to 1, it will basically be the numerator. Phi z at z equals to z naught. For m equals to 2 and higher power, then it will be expressing phi z at the m's minus 1th derivative of phi z naught and over m minus 1 factorial. So let me put some examples down here, if I could, for this. If I have a fz, actually, try to remember this, I guess. I'll try to erase top. So if I have a fz equals zq plus 2z minus over z minus I to the 3. See, this is in the form of phi z over z minus z naught to the nth power. For this case, m equals to 3. So it falls into this scenario. For the first scenario is in a way trivial, so let me show the next this scenario. So we need to do the second order since m equals to 3. So m minus 1 is 2. So we do the second order of z, which is, so let's do the first order derivative, which is 3z squared plus 2. Derivative of that will be 6z. So then the phi z naught will be phi double prime z naught will be 6 z naught. And we know z naught is I, then it will be 6I. So the residue will be 6I over 2 factorial. So it's 3I. And that's the answer for the function that have this type of form. Okay, let's do the same thing, the same function, using this formula. This formula is in a way more general, as long as you know a function that has a pole to the nth power. Basically, the pole, the nth power basically means if a function that orders to something like this. Basically, how fast it goes to 0. So this is, of course, higher k. This is basically, say k equals 3. This is k equals to 2. This is k equals to 1. So the bigger the k is, the faster. Bigger the k is, the faster it decays. So this is 3 because it's at time it's getting close to k, decays really fast. Okay, anyway, same problem. Let's see this. As you can see that, by observing it, we know that C will equals to I, because that's obvious the pole. And in order to have a finite derivative, of this, we will need the n equals to equal to 3, because otherwise the derivative will give us something with the form of this, and this goes to infinity because this is essentially limited to 0. So we need to make this finite. So I actually need to put it into this. We have to make this finite in order to make it work around. So we will have n is 3 already, we know that. So 3 minus 1 factorial limit z goes to I, the second derivative, and so this is multiplied z to the z minus I to the third power, then we will have so this is awfully looks like the one we already done here. This is just a simplified general form, but this is more. This is simplified specific, but this is more general form. So we have 2 and 6 z naught equals to I. Then we have 3I, which is same to the previous problem. And for this, if you want to know the integral, then of course it will be 2 pi I dot 3 I. We ended up having negative 6 pi. And that's the answer of the integral.